All right, so recording again. So I just wanted to get everyone started on the project, like I did for the last one. So here are the predicates that we're asking you to write for project 6. And then over here, I have a window with Prolog up, and I think what I will do here is try to make this, yeah. Okay, all right, so now it's a little bit more evenly split. Let's just write eval. So the trees in the project look a little bit different. There is no notion of an empty tree, just like there's no notion of an empty expression tree. The base case now is going to be eint. So this is a tree that just contains a single number, and that number is, whatever the second thing in the list is. And then we have 3 types of non-leaf trees. So those are the leaf nodes. And we have 3 types of non-leaf nodes where we're going to have eadd or esub or emul, and then 2 other things. So there's going to be a left-hand subtree and a right-hand subtree. So these are the types of these are basically the patterns that we care about. And so in Haskell, you had to explicitly do all these patterns. In Prolog, Prolog is much looser about types. And so we are potentially, for some of these, going to be able to write them using an underscore in this pattern rather than having to write out patterns for eadd, esub, and emul. So let's think about what the eval is going to look like here. So eval, so the first case is an eint. So what is the evaluation of a tree that contains a single integer? Well, it's just that integer, right? So that is the first part of this definition. And so we can go ahead and test this. So let's go ahead and load in the solution. So eval of an eint 4 is just going to be 4. So we have already gotten that base case handled. This will not work if we have a more complicated. So let's add 4, whoops, shoot. So let's eadd. So let's add 4 and 2. And I'm gonna need to add another bracket here. Okay, so this is 2 and 4 as leaf nodes, and then their parent is an addition node. And so we haven't written a definition for this, so Prolog can't find any value of x for which this is true. All right, so the pattern that we want to match here is going to be eadd, and then we're going to have a left subtree and a right subtree. So if you think about this for a little bit, this is going to have to be a recursive definition, because what we want to do is we want to evaluate the left-hand side, figure out what that evaluates to, evaluate the right-hand side, figure out what that evaluates to, and then we want to add those 2 numbers together. So let's do the recursive evaluation here. So this is going to be some value. Do we want to use x? X is not a great. We'll use x because that's what we used up here. So this is going to be true if, so we'll need to define x, but before we can get to defining x, we need to figure out what the evaluation of L is and what the evaluation of R is. So let's say that the evaluation of L is going to be LX, right? So the X from the left-hand side. And then we're also going to do this on the right-hand side. So the evaluation of the right-hand side is going to be RX. And so then what? So if we have LX, which is the evaluation of the left-hand side, and then we have Rx, which is the evaluation of the right-hand side, then X is just going to be the sum of those 2 numbers. So X is LX plus Rx. And maybe we'll put a space there to make that a little bit cleaner. Okay, so now with that definition, we should be able to run this, and it's going to say, well, one solution to this is 6. That's great. And if we ask it to find more, it'll never find any more. We probably don't want to add cuts here, because we'll add cuts during the in the testing functions. So if you look at test.pl, these are the testing predicates, and you'll notice that they all have cuts in them. It's probably a bad idea to add cuts in the actual definitions of these things. So you'll just have to kind of get used to telling Prolog, oh, you know, I don't need any more solutions because I know there's only going to be one of them. All right, there's another example here in the lab. So I'm just going to copy and paste that. So this is a longer, more complicated tree, but it's essentially a multiplication, and then the multiplication has an addition on one side, a number on the other, and then the addition has two numbers inside of it. So this is going to fail right now, right? Because we haven't written the case for multiplication. But the case for multiplication is basically going to be the same as the case for addition, except that instead of adding the two numbers, we're going to multiply the two numbers. So now that we have that definition, we should be able to get the value here. So let's think about, is that the correct value? So this is going to do 2 plus 3, which is going to give us 5, and then 5 times 4 is 20. So yes, that is correct. Okay, so now hopefully you can do the trivial generalization of this to E sub, right? So it's going to be just like this, except with a subtraction. And then hopefully this plus what we did in the lab with the binary search trees should allow you to figure out the definitions for count ops, which is very similar to count nodes, height, which is calculating the height of the tree, postfix, which is pulling out the expression into a list. We did this with strings in the other languages. We're doing this just with lists in Prolog because string manipulation in Prolog is really annoying, and I didn't want us to have to learn that. So we're just going to build up lists rather than converting them into strings. And then unique integers, where we're asking you to pull out all of the integers in the list. Okay, so I think at that point, I'm going to go ahead and cut the recording again. I think you have plenty at this point to go on to finish the project, so feel free to ask questions on Piazza if you run into trouble with this. But yeah, I think that that's all that I need to say about that. So good luck.